Section: Introduction. In this section, we explore how to enhance large language models, LLMs, by leveraging model interpolation techniques. We aim to improve the alignment of LLMs with human expectations through a method called EXPO, model extrapolation. The idea is to extrapolate a stronger model from two relatively weaker models without the need for additional training. By doing so, we can boost the performance of LLMs in line with human preferences. Our approach is inspired by the concept of model interpolation, where different fine-tuned models are combined into a unified model by adjusting their weights. We observed that by interpolating between models trained using different methods, such as supervised fine-tuning, SFT, and direct preference optimization, DPO, or reinforcement learning from human feedback, RLHF, we can achieve a balanced performance. This led us to question whether we can extrapolate a stronger model by reverse interpolating between two existing models. The EXPO method assumes that a moderately aligned model can be obtained by interpolating between a less aligned model, e.g., SFT model, and a better aligned model. By extrapolating from the weights of these two models, we can directly obtain a stronger model without additional training. Our experiments show that EXPO effectively improves the alignment of various LLMs, even surpassing fully trained models in some cases. It also enhances off-the-shelf models and demonstrates scalability across different model sizes. In summary, model extrapolation shows promise in boosting LLMs' alignment with human preference and maximizing their potential. We believe this method warrants further exploration in future research. Section Summary. In this section, we explore the concept of model interpolation to enhance large language models' alignment with human preference. By leveraging a method called EXPO, model extrapolation, we demonstrate that a stronger model can be obtained by extrapolating from the weights of two relatively weaker models, without additional training. This approach significantly improves the alignment of various language models, surpassing fully trained models and enhancing off-the-shelf models by up to 6.8% on benchmarks like Alpaca Eval 2.0, showcasing promising potential for future research in boosting language models' capabilities. Section: Insights on EXPO. In this section, we will provide insights on EXPO. We begin by using a figure to explain EXPO intuitively. EXPO can be thought of as a global gradient update that is based on the overall weight change delta theta equals theta underscore w from the initial m underscore w to the final m. The weight change delta theta points towards a direction in the parameter space where the model's alignment with human preference improves, as measured by a reward score. Therefore, EXPO aims to enhance the learned reward signal through the extrapolation alpha delta theta. From the illustration, we identify two prerequisites for EXPO. Firstly, the model M should not have reached its optimal training level yet. This condition is generally applicable, as even advanced models like GPT-4 are continuously optimized for better alignment. We will demonstrate later that even models extensively trained for human preference alignment still have room for improvement. Secondly, the weight change delta theta from m underscore w to m should be of high quality, indicating an accurate direction for alignment improvement. This quality of delta theta can vary based on the training setup of m and the capability of m underscore w. When the model m, initialized from its SFT checkpoint m underscore w, has undergone moderate alignment training, EXPO can potentially enhance its alignment. We will validate this experimentally. However, for other combinations of model checkpoints like base and SFT models or two separately trained RLHF models, the second prerequisite is not guaranteed. We highlight the appealing properties of EXPO: simplicity, efficiency, and scalability. EXPO is simple to implement and quick, involving extrapolation based on the weights of two checkpoints. It does not require additional model training beyond the checkpoints, and tuning the hyperparameter alpha is straightforward. EXPO can be applied to various large language models, including those extensively trained for human preference alignment. In our experiments, we showcase the effectiveness of EXPO by training the model M with limited preference data, demonstrating that EXPO can improve models trained with less data to achieve performance comparable to or better than fully trained models. To align models for human preference, we utilize the alignment codebase by Hugging Face and train Mistral-based -7B SFT full and -7B full models with varying data sizes. We employ the mainstream DPO algorithm for alignment training, using the SFT model -7B SFT full as the reference model and for initializing policy models. The models are trained on GPUs following a specific hyperparameter configuration. For our experiments, we use the preprocessed ultra-feedback dataset, a large-scale preference dataset commonly used for training aligned language models. The dataset contains instructions and response pairs with preference labels, and we train our models using this data. Section Summary. In this section, we provide insights on EXPO, which can be understood as a global gradient update, aiming to enhance a model's alignment with human preference by amplifying the learned reward signal through extrapolation. We identify two prerequisites for EXPO. The model should not be trained optimally, and the weight change from the initial to final model checkpoint should accurately indicate an improvement direction. EXPO is highlighted for its simplicity, efficiency, and scalability, showing promising results in improving models trained with less preference data and being applicable to various large language models. Section: Evaluation. In this section, we assess the models on Alpaca Eval 2.0, a well-known benchmark that evaluates how well LLMs align with human preferences. This benchmark includes 805 instructions that represent real user scenarios. Each instruction's response from the model being evaluated is compared directly with that of the GPT-4 baseline. A GPT-4-based evaluator produces the probability of preferring the evaluated model, offering a cost-effective alternative to human preference annotation. The win rate over the GPT-4 baseline is then calculated as the expected preference probability across all 805 instructions. Recently, Alpaca Eval 2.0 introduced the length-controlled (LC) win rate metric to address the length bias of the GPT-4 evaluator, which tends to prefer longer responses. The LC win rate metric shows a high correlation, Spearman correlation of 0.98, with real human evaluation, enhancing the reliability of Alpaca Eval 2.0 assessment. For our model, we determine the best parameter based on performance on the ultra-feedback development set, evaluated by an open-source reward model. This model ranks well on RewardBench, a platform that evaluates reward models' performance. Importantly, this reward model is not involved in preference annotation or training of the models we experiment with, reducing the risk of reward manipulation. We also provide the average scores generated by the reward model on the 805 Alpaca Eval 2.0 instructions for reference. In table, we display the performance of models trained with reduced preference data, 10% and 20%, and the results after applying EXPO on them. As expected, training with less preference data leads to lower performance, as shown by their LC win rates on Alpaca Eval 2.0. However, applying EXPO boosts the performance significantly. For instance, using only 10% of the data can achieve competitive performance compared to using 100% data, and using 20% data surpasses that performance. The model trained with 20% data shows a greater improvement from EXPO than the one trained with 10% data. We observe that the quality of the extrapolation direction is not solely determined by the amount of data. Using 20% data can outperform using full data when applying EXPO, as larger data sizes can amplify biases in the preference data, which the model may learn as shortcuts. We further analyze the impact of the model's training configuration on the extrapolation direction. Figure illustrates the reward scores and output lengths on the ultra-feedback development set for different EXPO extrapolation coefficient values. We note that the optimal coefficient varies with the data size, generally decreasing as the data size increases. The global optimal reward score is achieved with a medium data size, 20%, rather than smaller or larger sizes. Smaller data sizes benefit significantly from EXPO but are limited in providing an accurate extrapolation direction, while larger data sizes may learn spurious features as shortcuts, affecting performance. Section Summary. In this section, we evaluate our models on the Alpaca Eval 2.0 benchmark, comparing their performance with a GPT-4 baseline using a new length-controlled win rate metric. By applying EXPO on models trained with varying amounts of preference data, we observe that using only 10% and 20% of the data can achieve competitive performance to fully trained models, with the model trained with 20% data showing a greater improvement. The optimal extrapolation coefficient in EXPO varies with data size, with medium-sized data, 20%, achieving the highest reward score, indicating the importance of balancing data size for accurate model extrapolation. Section. Comparison with hyperparameter tuning. In this section, we compared EXPO with hyperparameter tuning by adjusting the learning rate and training epochs on 20% of the training data. We found that tweaking these hyperparameters improved the reward score but still fell short of the optimal score achieved by EXPO. This adjustment also hindered the gains from model extrapolation, likely due to overfitting and learning spurious features like length bias, leading to inaccurate delta, theta. Models trained with higher learning rates or more epochs tended to generate longer outputs with small alpha but did not show significant reward improvement, indicating that delta, theta, likely contained spurious features rather than true human preferences. We highlighted the importance of selecting the right training configuration for M to ensure the quality of delta, theta. Additionally, we discussed how the capability of M_W impacts the effectiveness of EXPO in the subsequent sections. We then demonstrated the effectiveness of EXPO in enhancing off-the-shelf LLMs from Hugging Face, emphasizing its scalability across different model sizes and capabilities. When selecting LLMs for experiments, we faced challenges with the opacity of some well-known models, leading us to choose open-source DPO, RLHF models with publicly accessible SFT checkpoints and disclosed training data. The experimental results showed significant performance improvements across various LLMs, indicating that most open-source LLMs can benefit from further alignment with human preferences through EXPO. The results in the table illustrated that EXPO boosted the performance of already aligned LLMs, with notable increases in win rates on Alpaca Eval 2.0. The enhancement was observed across LLMs of different capabilities, suggesting that EXPO can unlock the full potential of these models. Particularly for the Tulu 2 model suite, the improvement by EXPO scaled up with increasing model size, indicating that a larger and stronger M_W can lead to better learning of reward signals and more accurate delta, theta, resulting in greater improvements post-model extrapolation. This implies that as the capability of M_W increases, the benefits of EXPO are expected to scale up as well. Section Summary. In this section, we compare the performance of our EXPO method with hyperparameter tuning by adjusting learning rates and training epochs on a model. While tuning hyperparameters slightly improves the reward score, it still falls short of the optimal score achieved by EXPO, indicating overfitting issues and the importance of the model's configuration. Additionally, we demonstrate that EXPO significantly enhances the performance of off-the-shelf language models, showcasing its scalability across different model sizes and capabilities. Section. Discussion. In this section, we will discuss the impact of different model choices for M_W and M on the effectiveness of EXPO. In our previous analyses and experiments, we selected M_W as an SFT model and M as the model further trained to align with human preferences based on M_W. We explore whether other combinations of M_W and M, such as a base model and an SFT model, or two separately trained RLHF models, can generate meaningful extrapolated models. We conducted experiments with various combinations: base plus SFT, SFT1 plus SFT2, trained from different base models, SFT1 plus SFT2, same base, RLHF1 plus RLHF2, same base. Our results show that extrapolating from two SFT models trained from different base models can lead to model collapse due to a lack of mode connectivity, which requires the same or similar initialization. When combining base and SFT models, extrapolation leads to performance degradation because the transition from base to SFT does not naturally capture human preferences, necessitating additional alignment training. The SFT model acquires instruction following abilities and adapts to specific input-output formats, which can be amplified by EXPO, but this amplification may not aid in alignment and could also lead to model collapse. For separately trained SFT or RLHF models, we observed that they do not benefit from model extrapolation, likely because M is not initialized from M_W, preventing the amplification of reward signals in the parameter space. Even if M has not reached optimality on its optimization path, it cannot improve in a different direction. Currently, our EXPO method is most effective for the combination of an SFT model M_W and a model M, further trained on top of it, which is a common choice as modern LLMs aligned with human preferences are typically initialized from their SFT checkpoints. LLM alignment. Modern LLMs are initially pre-trained on large textual datasets to create a base model, then fine-tuned to align with human expectations through supervised fine-tuning, SFT, and learning human preferences through reinforcement learning, RL, or contrastive learning. Scaling up alignment data and training iterations can enhance model capabilities, but finite resources may limit full exploitation. Our EXPO method aims to boost LLM alignment with human preferences efficiently and effectively. Model merging and interpolation. Model merging integrates multiple fine-tuned models from the same base model to create a unified, strong model. Model interpolation blends model weights to improve capabilities, with uniform interpolation often resulting in trade-off performance. Our EXPO method blends model weights to enhance model strength beyond fully trained models, aiming to surpass limitations.